There's really no need to say this, but my programming skill's a gift. This is disconnect path in a binary matrix by at most one flip. Kid. Okay, so you're given a zero indexed m by n binary matrix grid. Okay, so what does it mean for a m by n matrix grid to be binary? Well, that means that each of the individual grid cells either have the value 0 or 1. Okay, you can move from a cell row call to any of the cells row plus 1 call or row call plus 1. Okay, so you can either move to the right, which corresponds to going to the next column, or you can move down, which corresponds to going to the next row. Okay, so this is kind of a constraint of this problem, which is interesting because usually when you think about moving, right, I can move right, I can move left, I can move up, I can move down, but in this particular problem, there's a strict constraint which that you can only go right or down, right? Those are your only two options. The matrix is disconnected if there is no path from 0, 0 to m minus 1, n minus 1. Okay, what does it mean for the... Okay, so you can only move to a cell that has the value 1, right? So if you're somewhere, and of course you can only move right or down if the cell value to your right is 0 and the cell value of the cell below you is 0, then you have nowhere to go, right? You're stuck because you can only go right, you can only go down, but you can only go right if that right cell's value is 1. You can only go down if that down cell value is 1, but if they're both 0, you're stuck. So there is no path, at least at that point, right? And you could see that maybe at all points there's some situation where there's no path. Okay, now you can flip the value at most 1, possibly none cells. You cannot flip the cell 0, 0, and m minus 1, n minus 1. Okay, so maybe, there's almost a path, right? Maybe there's a path where it almost connects, but then there's one cell in the center where the value is 0, so you could flip that to 1 to make it connected. Or in the other case, maybe there's only one path from the source to the destination. If you want to make it disconnected, you could take one of those cells with the value 1 and turn it to 0. Now you've kind of choked. You've removed that path, right? Because you cut off a part of that path. Return true if it is possible to make the matrix disconnect, or false otherwise. Note that flipping a cell changes its value from 0 to 1 or from 1 to 0. Okay, so this is kind of weird, right? Because we want to take a grid. All right, so this problem is kind of confusing because it goes against usually what we're trying to do, right? Usually we're trying to like connect things, but this is basically saying, can we disconnect this graph? So what would it mean for the graph to be disconnected? Well, that would mean there would be no path from 0, 0 to m minus 1, right? Because you're trying to find a path from 0, 0 to m minus 1. So is it possible that there is no path, or that you could flip a bit so that path goes away? Or the remaining case is that there's no way that you could disconnect this graph, right? There's just too many ways that you could go from 0, 0 to m minus 1 and m minus 1. And in that case, nothing you do will make this work. But if that doesn't make sense, let's just go ahead and walk right into this. So let's look at this example problem. And that'll probably help us just a little bit because I'm rambling a bit. So if we had 1, 1, 1, I'm just drawing out this example graph. 1, 0, 0, 1, 1, 1. Well, obviously the path through this system, right? There's a path here. If you wanted to get from the top left to the bottom right, which is the solution, right? I mean, that's the purpose of this path. If we were to change this cell to 0, right? Well, then there would no longer be this path, right? This path will get removed because now there's this whole row of zeros, right? Now, since there's this whole row of zeros, there's no way that we can make this work, right? So really what this problem comes down to is, can you make... Interesting. I just thought of a new way of solving this problem on the spot, but I'm not going to cover that. But damn it. It's always funny when you walk through a problem and you think of a solution. I just thought of another solution, but it's ridiculous. But right, so here, right, now there's no path, right? Because this thing can go all the way right? But if you start here, there's no way that you're going to be able to pass this row of zeros, right? So you're stuck. So you can't travel to that next row. So there's no way for you to get to your destination path. So that is true, right? So it's true that we can change at most 1 bit, right? We change this bit. We can change at most 1 bit and make it such that there is no path from 0, 0 to m minus 1, n minus 1. Now this problem is different, right? Because in this problem, well, what's going on? Well, since this bit is 1, let's get back to object eraser. So for this second example, why is it false? Well, you'll notice that there's multiple paths to the destination, right? So if I were to change this value, right? Okay, guys, so I just decided that I'm going to do this the second way I thought of. Well, that way's actually slower. No, I'm going to do it the first way. Okay, so we change this one to 0. So we change this one to a 0. There's still this path, right? So it's like, okay, well, then let's change this other one to a 0. Well, if you change this one to a 0, there's this path, right? So no matter what you change, this person starting at this cell has options. They have two options. They have two options to get to the destination. So since they have two options to get to the destination, regardless of what they choose, regardless of which cell you decide to change the value to choke that path, right, to destroy that path, they can just use the other one, right? So since they can use the other one, they always have two options. You can only change one of them. You're out of luck. There's no way you can disconnect them, right? You change A, they go down path B. You change B, they go down path A. So really what this problem comes down to is three different cases we need to think about. And these two systems kind of articulated two of those three cases. Well, what are these three cases? And we'll look at it with respect to a 3x3 matrix, okay, for example. So the first case, I guess, is, well, there is no path, right? If there's no path, then we return true. It's possible that the system, for example, looks like this, right? If the system looks like this, now I'm going to draw a corresponding graph with just edges, or with just connections, so we can see kind of more what this looks like, right? There is no path from 0, 0 to n minus 1. So in this case, we're good, right? We're good in this case because there's really nothing that we need to change. We don't need to change anything. These people are just disconnected. There's no path, so we return true. We don't need to change any grid cell, okay? So that's the first case, and that's good. And let's just erase this so things are a little bit more clear. The next possibility, right, if we're going to exhaust all possibilities in terms of paths, okay, there is one path, okay? Now, if there is one path, what does that look like? Well, let's just do an example like this. In this example, we have a path that looks something like that. And in this case, we can also ensure that there's no path because we can do what? What can we do in response to this? We can destroy the single path, right? If we destroy the single path that exists, right? If I was to X this out, that would X this out, and then there would be no path between them, right? So if there's only one path, we can change one of the grid cells' values to 0 to destroy that path, right? So if there's no path, we don't have to do anything. If there's only one path, we can just destroy one of the values in that path in order to make that path no longer exist. So we can also handle this, right? So in this case, it's true that it's disconnected. In this case, it's true that it's disconnected because we can just change one of the cells in the path. Now, what is the final case? Well, we've done the case where there's no path. We've done the case that there's one path. So I suppose the final case, if we thought logically, is there's more than one path, right? That handles all possibilities. There's either 0 paths, there's 1 paths, or there's more than one path, okay? So there is, so the final case is there is more than one path, okay? So what would that look like? Well, that would look like that final example, for example, let's do it here. So perhaps here, right, in this system, we have a graph that looks like this. So there's this one path here, but there's also this other path here. So now, like in the example, because this is the example exactly, we know that there is no way to disconnect this graph because it has two possibilities. If we delete A, it goes through path B. If we destroy path B, it goes through path A. So we don't really have a way of handling this, and in this case, it would be an X, okay? So this seems pretty simple, right? It seems simple enough. We just need to run some sort of algorithm to find the number of paths that we can find from source to destination. Now, there's a bit of a caveat, right? There's a bit of an exception that you need to think about in order to determine the number of paths, okay? Now, this is where I first made a mistake when I solved this problem is, well, I'm looking at an example in terms of these systems here, right? Well, in these systems here, this is obviously one path, right? And this is obviously two paths. But what about something like this? Okay, this would mean that, you know, this corresponds to, let's just draw it out, you know, 1, 1, 1, 1. Let's extend this system out because technically, so let's do a 4x4 example. Okay, so we did. Sorry, my tablet moved. We can go down and down. So imagine we had a system like this, right? Well, what does this mean in terms of the paths? Well, on initial look, right, you might say that this is two paths, right? You might say that this is a two-path system because obviously there's two different unique paths that I can take to go from the source to the destination, right? I could take this path or I could take this path, right? So you might say, well, this is a two-path system, so therefore, since it's a two-path system, I have to return false because if I destroy path A, they'll take path B. If I destroy path B, they'll destroy path A. They'll take path A. The problem is, though, is that I could change this cell to 0, right? I could change that cell to 0, and it would still be true. It would be disconnected. So why is that the case? Well, the issue is even though there's two unique paths through this system, there's still points of which the paths share a point. And since they share a path at that point, if I delete that point, then they are no longer connected, right? If I had two paths, like a red path that went like this, and a green path that went like this, right? And well, let's do it a little bit different, actually. If I had a green path that went like this, and a red path that went like this, right? These are two unique paths. But if I were to just intelligently, right? If I was just to delete the path of which they share, right? If they share any point, right? If these two paths intersect at any point, I can disconnect them, right? I can disconnect both of them, right? If all these paths meet at one place, then I can just disconnect them. And if I can disconnect them, then they're all mutually disconnected, right? I just ruined both of these paths by deleting one cell because they intersect. So the only way these two paths, the only way I can't disconnect them by just removing one cell is if these two paths are completely disconnected, right? If these two paths are completely disconnected, then well, I can't destroy both paths. I can destroy this one, but then it comes down to that A-B thing again, right? If I destroy this one, then they can use the green path. If I destroy one member of the green path, they can use the red path. So the issue here is that there's an intersection point between these two paths, right? Since these two paths intersect at a point, I can still destroy them, right? Since I can take these two paths and they intersect here, right? Just even though they're two unique paths in terms of they take different routes, since they have an intersection point, I can remove that intersection point and then it disconnects both of those paths. So what this really comes down to, right, is Well, there doesn't matter how many paths there are, right? Because there could be a bunch of paths, but if they all intersect at some point, that's the choke point, and I can erase that, and there's really no connection between the source and the destination. So really, it's not about there being more than one path. It comes down to there being more than one what's the word I'm looking for? There's no more than one path with no intersection, I guess, with zero intersection. So that means I need multiple paths that don't intersect at any point, except the source and the destination, of course, right? Because you can't change the source to 0 and the destination to 0, right? In this example, since there's an intersection here, I can delete that intersection between these two paths, right? These two paths share a point here, so I can delete that point. But if these paths, if we had the case where these paths looked a little bit different, right? If these paths instead had no intersection points besides the source and the destination, right? Regardless of what it looks like here, well then, now they're two non-intersecting paths. So I don't have that choke point, right? They're now in this arena here, right? There's this path and there's this path. There's no intersection. So since there's no intersection, then I can just, there's nothing I can do. I can't, if I delete one, they'll use the other. If I delete the other, they'll use this one, right? So that's kind of the nature of this problem, right? If there is no path, we're good. If there is one path, one non-intersecting path, right, I guess, but if there's more than one path that doesn't have any intersections, then it's false, right? So how do we manage this then? Well, if we wanted to find two non-intersecting paths, that means that they're independent of each other. So if they're independent of each other, if I destroy this entire path, it's not going to affect the green path, right? So if these paths are truly non-intersecting, if I delete one of the paths to the destination, the other path should exist, right? Because they're not intersecting. So since they have no intersection, one doesn't affect the other, right? Versus if these paths do have intersection, right? If these paths do have an intersection point, then once I delete one path, you'll notice that the other path is now also disconnected. So if I find one path, delete it, and I can find another path after I've deleted the first path, that means there's two paths that are unique that don't depend on each other, okay? So the idea is really, we want to find we want to determine, right? Because all we need to determine is that there's at least, if there are at least two non-intersecting paths, right? That's what we need to determine. So how can we do that? Well, one way to do that is so they don't intersect, then deleting one doesn't affect the other. So that's kind of the observation, right? They have no intersection. So if I delete all of this path, it's not going to affect the other path because they don't intersect. So all we need to do to determine if there's two non-intersecting paths is, 1, find a path. 2, delete that path. 3, find a second path. Right? Because if there's a second path when we delete the first path, that means that second path wasn't affected by the deletion of the first path. Therefore, that second path is completely independent of that first path. All right, I'll say that again. If you can find a path and delete it, that means that whole path is gone. If you can find another path, that means that that second path is completely independent of the first path that you just deleted. So that means there's two non-intersecting paths. Okay? Now, if you can't find the first path, Well, that means you're in case 1. If there's no first path, then you don't have to do anything. You just return true. If you delete that path and you can't find a second path, well, that means that you're here. You can't find the second path, so there must be only one non-intersecting path, so you return true. If you can find a second path, right, you find a path, you delete it, you find a second path, that means that there's 2 independent paths, so you return false. So how do we find paths efficiently? Well, to do that, we'll just run depth first search, right? We'll try to find a path following these movement rules, and then we'll just back propagate until we can't anymore. So maybe just to go through a quick example, right? What we'll do, for example, like this, is we'll find a path in this grid cell by asking our neighbors if they found a path. This neighbor will say no. We'll go down. This system will say, yes, I found a path to the destination. So it'll keep this as 1 because we don't want to change that. But we'll change this to a 0, right? Because since it found this path in this grid, right? So it'll find this path in this grid. And then we'll change all these corresponding cells to 0. And then we'll ask if it can find another path. And it won't be able to, of course, because we've deleted the one path that exists, so we return true. Another example, 1, 1, 1, 1, 1, 1, 1, 1. Perhaps using DFS, we find this path. So we delete this path. We set it equal to 0, 0, 0. And then when we run DFS again, we find another path. So that must mean that there was a second path that's completely independent of the first path. So deleting one grid cell won't result in disconnecting this graph. Okay, so let's go ahead and do that. So we're going to have to run DFS on this system. So let's go ahead and do that. Now this will use I and J to represent the positions, right, of the grid cell that we're looking at. If I equals length of grid minus 1, right, because that's the destination. So we'll call destination length of grid minus 1. No, we'll just do it here. If I equals length of grid minus 1 and J equals length of grid 0 minus 1, that means we made it to the end. So we return true. Okay. That means we made it to the destination. But if we're in a position that isn't actually a position in the grid, right? So if not 0 less than or equal to I, less than or equal to length of grid. So if we aren't in an actual position within the grid, or not 0 less than or equal to J, less than length of grid, 0, with M by N. Or we're in a position where there is no, put myself over here for now. So if we're in a position where, we can't travel to this position because it's a 0, right? If you're at a 0, that means what? That means you can't traverse this cell because you can only traverse cells that are non-zero, that are 1. Okay, so if this is the case, you return false. So we're in a spot, we're either in a spot that doesn't exist on the grid or we're in a spot where the value is 0. Otherwise, we're going to traverse this cell. So we might as well set this cell to 0, right? Because either we set this cell to 0 because it finds a path, or we set this cell to 0 because because of what? We either set this cell to 0 because it finds a path, or we set the cell to 0 because it doesn't find a path, so we might as well set it to 0 so that we don't try to traverse it again because it's a useless series in terms of the path we're trying to travel. Okay, so we return if any of our neighbors can reach the end of the grid cell, right? And if they can, it'll set everything to 0 on the way up. So return DFS KL for KL in, well, we can go down or we can go right. All right. So we'll run DFS once. We'll notice that the way that this works, it ends up setting grid 0, 0 to 0. So we'll reset grid 0, 0 to 1 because it's going to set the whole path to 0, including 0, 0. But you can't change 0, 0, right? Because 0, 0 is always a choke point because everyone starts at 0, 0. So we have to reset that as 1. And then we just say, well, if we can find another path, that means that we can't disconnect it, right? So if this returns true, that means it found another path. So if it found another path, we want to return false, right? If this returns false, it wasn't unable to find another path. That means it's disconnected if we remove at most one, if we flip at most one grid cell. So if this returns false, that means we return true. If this returns true, we return false. That's why we throw in the not. Okay. All right. Let's go ahead and run that. Okay, cool. Now, something you might be wondering, which I also wonder when I walk through this, is like, imagine you had, what if one cell's path, right? There's no way for you to choke another path without intersecting with that path, right? Because the thing you might worry about is like, what if you delete one whole path and then there is another path, but that path can't work anymore? Is that possible? Well, it's not possible because, if you deleted one whole path, it has to be independent of the other path. And if you delete that path and it affects the other path, that means they're not independent. It was a worthless reason to explain that right now. But if you're thinking about that, just think about the fact that these paths have to be independent, right? So in order for them to be independent, if you traverse one, it can't affect the other, right? And you're only trying to find one such path. So in finding that one such path, it's not going to affect the other path that you're trying to find, right? Like, if you go down a rabbit hole and find a path, you're only going to find one such path. You're not going to affect the other one, right? Because DFS is going to keep trying to go down one path until it can't. So it's going to go until it finds a path. It's never going to, like, partly cover two paths, right? Like, if you had two paths... Okay, maybe this makes a little bit more sense. Sorry, I'm rambling here. But if you had two paths like this, right, or any sort of, like, I don't know, something in the middle too that isn't connected. Imagine there's some grid cell that looks like this, right? You might be worried, like, what if I accidentally delete some of this path as well as this path? Well, that won't happen, right? Because DFS is going to keep trying to go down a path, right? DFS is an implementation where you're always trying to keep going down the path that you most recently tried, right? You use a stack with DFS because if I try going down this way, I'm going to keep going down this way until I try everything I can going down this way. So I'll never affect the other path, right? Versus if I go down this way, I never like start going down this way with DFS and then try to go the other way. No, I go this way until I either get stuck, which means that I might as well erase it, because if I get stuck, all those ones are worthless because it doesn't get me to the path, to the destination, or I get to the destination and the other path is intact, right? So with DFS, setting things to 0 will never affect the other path if that path is truly completely disconnected from the path you're looking for, or whatever. Okay, so what is the time and space complexity of this algorithm? Okay, so for, let's say n is the length of grid, and m is the length of grid 0, so the number of columns, the number of rows. Well, for time, well, we have to run DFS. Now, technically, DFS, you can think about it as taking m times n time, right? Because you have to look at all the grid cells. But a caveat with this problem is we can only go right and we can only go down, right? So since we can only go right and down, at every iteration, I either have to increase the row that I'm at or increase the column that I'm at. So I can look at most, row plus column grid cells, right? Well, let me think of a problem where I think that's right, but let's see. So I'm trying to think of a counterexample where this could be really slow. So it could be that I go down, I have to check all this, I don't find the path. I go down, I check all this, I don't have to find the path. I go down, I check all this, I don't find the path. I go down this, I don't find it. I go down. So I could technically look at all grid cells, if almost all grid cells, if the problem was set just incorrectly, right? If I had one, I could end up looking at all of these cells. For example, I'm trying to think of an example where it's m times n and not m plus n. So in this example, I would do m times n minus 2, but that's proportional to mn. So I could still look at almost all of the grid cells. So it's not m plus n, it's m times n time, unfortunately. And then in terms of space, well, I don't have to create any additional variables, but I have to use stack space every time I run DFS, right? So I'm going to have to add all m times n stack space, because I could add all the grid cells, technically. Yeah. All right, guys. This time, there might be a tighter constraint here, but I think that's fine. All right, peace out.